This video is intended to protect you, the steam system operations worker, from the violent piping event known as condensation-induced water hammer. This destructive behavior of steam in piping can occur in a piping system that contains any condensable vapor fluid. The most common is steam, and is the subject of this presentation. Condensation-induced water hammer, or steam void collapse water hammer, can occur any time you try to fill a water-filled line with steam or a steam-filled line with water. Normally, in a steam system, you would not have water fill lines, but condensate can accumulate in low-point or dead-end steam lines, and if allowed, can result in destructive consequences. We will present some configurations which can potentially cause damage, take a look at how to minimize its consequences, and present a list of recommended do's and don'ts. The consequences are great and sometimes fatal when condensation-induced water hammer occurs. History holds several incidences of the condensation-induced water hammer in many complexes. In 1974, at the Indian Point No. 2 steam generation plant, a cracked feed water line resulted in an extensive investigation and tests. No personnel injury. At Tihange, France, a similar steam generator condensate to an active steam generator caused extensive damage. The pressure pulses reached 6,000 psi, which blew off the pressure transducers. No personnel injury. In 1986, at the Department of Energy Brookhaven National Lab, condensation-induced water hammer injured 2 workers and caused 2 fatalities. At the Idaho Chemical Processing Plant, located in the DOE Idaho National Engineering Lab, a 2-inch pipe fitting was fractured, causing the pipeway to fill with steam, as well as setting off an emergency fire evacuation alarm. The building was evacuated and operations disrupted. No personnel injury. And in 1993, at the Department of Energy Hanford site, a valve body was fractured by condensation-induced water hammer. The result? 1 fatality. The descriptions which follow can be applied in general to a wide range of steam system piping configurations. However, specific attention is given to a section of an actual steam piping configuration where a serious incident of condensation-induced water hammer occurred recently. In this event, it caused fracture separation of a valve, which then initiated explosive decompression that resulted in the fatal discharge of a large amount of high-velocity hot steam. A horizontal pipe that contains a reducer is shown in this illustration. This is a typical piping configuration that exists in the piping system of a steam plant. You do not necessarily have to have a reducer in the pipe for condensation-induced water hammer to take place. The steam could be either flowing over stagnant water in a pipe or in a condition in which both steam and water are flowing. The flow can either be concurrent, where the steam and the water flow in the same direction, or it can be countercurrent, where the steam flows against the water flow. Condensation takes place at the interface between the 2 layers. If a pipe is inclined downwards, a fluid flowing in a partially filled pipe will always develop waves. The waves trap steam between peaks, and the void collapses instantly. This will occur with steam which is stagnant or flowing in either direction. Water hammer has been experienced with lines at a downward sloping angle of 35 degrees. The steam simply gets sealed between waves and condenses and develops a high-pressure pulse from the collapsing void. When water is introduced into an active steam pipe, the flow can become unstable due to several factors. One is a high relative flow between the 2 phases of condensing steam and the water. Another important factor in this phase is condensation at the large interface between the water and steam. These combine to disturb the flowing stability, which causes waves to form at the interface. These waves grow until they hit the whole cross-section of the pipe, which then traps steam in between the wave peaks. As shown in this sketch of the same pipe reducer configuration, the disturbance causes the wave growth to fill the whole cross-section, which traps the steam behind it. Once the steam is trapped, rapid condensation takes place at the interface, which collapses the steam volume. As it collapses, the pressure at this location instantly reduces to near 0, thus forming a large pressure difference with the system pressure, which is behind the water slug. This large pressure difference becomes the driving force that speeds the water toward the lower pressure, therefore forming a traveling slug of water. This action becomes rapidly repetitive, and in this process, a series of accelerated water slugs travel back and forth between locations where there are changes in pipe diameter or direction. At these locations where the slugs are forced to change direction, they impact and form dangerously high local pressure pulses. The obstacle can be in many forms. A change in the pipe cross-section, which in this case is the reducer, a T, a valve, an elbow, or it can be a region where the pipe is fully filled with water. The banging sounds of these pressure pulses is the water hammer that is induced by the condensation. You have seen how condensation-induced water hammer develops, and its potential for causing high-pressure pulses. Let's examine the necessary conditions for water hammer to occur.
First, there must be condensate and steam in the piping system.
The second condition is a means to produce the pressure difference to accelerate the slug. And finally, the water slug must impact a water-filled section or a change in the piping configuration, for example, a T, a reducer, a valve, or an elbow. A few piping configurations which are likely candidates for condensation-induced water hammer are described as follows. One of the worst configurations is a vertical loop in which condensate can dangerously form a seal in the upstream vertical leg. The steam will move up the vertical section in bubbles, which collapse continually with extremely large pressure pulses. This can keep up for a considerable length of time. Likewise, steam replacing water in a long section of the line, even if it's level or sloped, runs along the top of the water, which initiates waves that quickly isolate pockets of steam. These pockets will collapse again with extreme pressure pulses. Another possibility is the accumulation of condensate that becomes trapped in the bottom of a sagging line. In this configuration, the steam is being supplied from the left-hand side and condensing on the downstream side. A steam void will develop and collapse. In reaction to the local pressure pulse, a slug of water will be accelerated in the pipeline until it reaches a change in section, a T, or an elbow, where the sudden deceleration of impact causes a high pressure pulse. In all, it is important to be mindful that steam and water cannot be safely mixed in a piping system without risking condensation-induced water hammer. Do not mix steam with water, either by injecting water into a steam system or steam into a system that includes water or condensate. Condensate should be assumed to be in all low points and dead legs until proven otherwise. We now know how condensation-induced water hammer occurs and what the consequences are. There are 13 recommendations for safe operational procedures that you should be aware of. Review and inspect all steam systems to ensure proper distribution and sizing of cold traps for startup and operation, and that all low points have steam traps. Give maintenance the highest priority. Frequently inspect all steam traps to ensure that they operate properly and that no condensate accumulates. Immediately repair or replace erratic steam traps. Use thermocouples where feasible to locate condensate accumulation. Do not use the method of cracking open the valve to avoid condensation-induced water hammer. This will not guarantee safe operation. The formation of a condensation-induced water slug can occur at very low condensate flow conditions. Valves and pipelines which lack properly positioned steam traps should remain open at all times, or preferably should be removed from the piping system. Before opening valves and steam lines, check for adequate placement of steam traps. Verify that the steam traps operate properly, and fully open the bleed valves, using a reduced system pressure to remove any remaining condensates. Where feasible, operate the valves remotely, using mechanical extension linkage, reach rods, or adequately controllable power-operated valves. Inspect the piping system for sagging. Where necessary, install steam traps or repair the sagging. Check and repair the piping insulation. It will save energy and reduce the accumulation of condensates in the piping system. Activation of cold steam piping should be performed slowly, at reduced pressure, and with trap bleed valves continuously open. The above list of recommendations should be followed, regardless of piping size. Do not exclude small pipe sizes without an appropriate analysis. All isolation valves are to have bypass systems. However, bypass operation will not prevent water hammer if condensate is present. Placement of blowdown valves before and after a vertical rise, such as over a roadway, is required to prevent possible condensate accumulation. Improperly designed steam water systems should not have the incorrect features overcome by operational methods. The systems must have the incorrect features corrected. The use of any condensable vapor-liquid mixture in a piping system is capable of generating condensation-induced water hammer and its destructive consequences. Training is aimed toward understanding the steam-water process because it is widely used in piping systems and has been extensively studied. This steam-water interaction can be violent and can cause explosive damage to steam system piping. Most importantly, it can cause injuries and fatalities if people are unaware of it and do not handle the procedures cautiously. The preceding list of recommendations is a summary of actions that should be followed to minimize the destructive consequences from condensation-induced water hammer. Please remember that when you become confronted with this steam-water interaction of condensation-induced water hammer, it is up to you, the operators, and the piping system managers to make sure that safety is the #1 priority. Ongoing training and alert operations will save you from a potentially tragic event. Report all suspect situations immediately.
Remember, under the conditions described, condensation-induced water hammer will occur. Its destructive consequences can be minimized by following the simple recommendations identified in this video.
Welcome to Schimberg Company. Schimberg Company is very proud to sponsor this condensate-induced water hammer tape. This tape is meant to be for your safety. This is a very dangerous subject that we deal with every day in our steam systems. Our steam systems can be taken for granted as we open valves, turn processes on. The danger is lurking out there all of the time, and we have to be constantly aware of it. Because of this danger, Schimberg Company, a few years back, decided that for our own personnel's training and for training of our customers, we built a working steam lab at our facility in Cedar Rapids. Our facility includes an electric 325 pound per hour boiler capable of producing 250 psi steam. Our system can show a lot of things. We can demonstrate traps, we can demonstrate pumps, steam coils, we can test equipment. We have a lot of various equipment that we can demonstrate here in Cedar Rapids. Our steam pressure today, we're operating at 150 psig. Our steam can go through multiple systems. Today we're using it to demo our steam-driven water hammer display. We take our steam off of our boiler at 150 psig. We reduce its pressure to 22 psi. At that point, we run our steam through a steam coil in this tank, and we inject cold water over the top of that coil to condense our steam. The condensation that happens in this tank produces hot water. We're maintaining our water today at 165 degrees. The hot water is fed into the bottom of our water hammer display. Our steam continues on after the coil, goes into a pneumatically operated control valve, which reduces its pressure to 1 psi. That's 1 psig of steam. That's very, very low pressure. Our control valve is controlled by a pressure transmitter with a single point loop controller. Our steam comes through. We reduce from 2-inch Schedule 40 pipe to 1-inch. Our pipe comes through a globe valve that we have rate set for flow into our water hammer display. We have a 1/2-inch check valve here that has a 1 psi spring in it. So if we do get any steam pressure spikes from our control valve, it is released to atmosphere. Our condensate demonstration is using Pyrex glass that is rated at 100 psi and 200 degrees F. We have our glass set up so that we maintain a water level in the bottom of our glass for the purpose of this demonstration. Our eccentric reducers at each end are installed backwards to help us maintain that water level I was speaking of. Our hot water comes up from the left into our vertical glass. As our water hammer happens, the water is then pushed out and recirculated back to our tank. This is a 125-pound cast iron 10-inch gate valve that Schimberg Company received back from one of our customers. This valve was installed on a 30-pound steam system. You can see the effect of condensate-induced water hammer. One of the operations people was opening this valve, turning a cold system on. After a few turns of the handle of this valve, the condensate slug went downstream of this valve, hit a T. The condensate slug then came back and caused local water hammer at the bonnet or gate of this valve. You can see the rupture that has ruptured the whole bonnet as well as the body of this valve. This is our condensate water hammer demonstration. We're on the opposite side while it's running with safety glass between us. As you can see, our steam is coming in from the right side of your screen. We have 1 psig steam is what we're aiming at. The highest that we see our steam pressure get is like 1.3 psig. Typically it's right around 1. Our water is coming in at a very slow rate. If you watch across the top of the water level, you can actually see the steam vapors. Steam vapors are white in color, so you can actually see them go across the top of the water. There's two forms of condensate-induced water hammer. The first, which is most common, is when you have a liquid level in the bottom of a steam trap. That interface is just like wind over the top of a lake. With low pressure, with light wind, you get small waves. With strong wind, you get white caps. With just 1 psig, you can see how the steam is picking the water up on the bottom and sending it downstream. As you're watching this display, keep in mind this is 1 psig steam. Imagine a steam line with 150 psig steam, or even 30-pound steam. The nature of condensate-induced water hammer is very violent. We are standing on the opposite side of a wall with glass behind us, and you can hear the water hammer take place. Our eccentric reducers I pointed out at either end is keeping a small water level in place. As we developed this demonstration, we broke numerous pieces of glass. We installed vertical T's with caps on top to act as a suppression device. As we have ran this demonstration for different training sessions, we broke multiple pieces of glass. The water hammer can happen in numerous places in this demo. As you can see from watching our water hammer demo, the waves in our glass pipe happen in various locations, typically not the same every time. Our gauge that we have on this demonstration today is a 30-pound gauge. We have trouble keeping gauges on this system, as you can imagine. With our gauge in operation, the highest spike that we have seen is a 14-pound spike. So that's a 14 psi spike at that gauge. Where condensate-induced water hammer causes such an unknown problem to us, and typically is what causes injuries and fatalities, is that the localized pressure that can be generated by condensate-induced water hammer can be thousands of psi. We've heard terms from the Department of Energy, from several experts, that those pressure spikes can be 1,000 to 1. As I mentioned, there are two forms of condensate-induced water hammer. The type where the steam is picking the water up, causing a wave, and that wave or slug of condensate is hitting a stationary object. The other type of condensate-induced water hammer is when you have an isolation valve shut off or a static condition occur in a steam system, a steam void is created. When the valve is then reopened or condensate starts moving in your system, at that point the void collapses. This creates extreme velocities and pressure spikes, and as soon as that velocity hits a elbow, a reducer, another valve, that's when the dangerous situation happens of condensate-induced water hammer. What we're showing here is a demonstration on steam quality. Because all of our piping is done in stainless steel and it's nice and pretty, we did not insulate. What we want to demonstrate today is how poor a steam quality you can have with a very short portion of piping either uninsulated or very long runs of piping. As you can see, the steam on this piece of paper is very wet. What we have is our steam pressure coming through at 25 psi. We have a impingement type steam separator. Separators are made in various types, but are usually used to improve the quality of your steam for your processes. This particular steam impingement device, the steam comes through it, hits a baffle plate, and drives the water down into a steam trap, and then it's discharged back into your condensate return. Right now, as the steam quality you see it, this is our steam quality coming directly from our boiler, and you can see how wet it is. Now I'm going to turn on the steam trap for our separator so that you can get an idea of what true dry steam or high quality steam is. The noise changes a little bit as your steam gets drier. But as you can see, with good dry steam, my paper is nice and dry. This is a glass cutaway of a steam trap. This particular trap happens to be a bucket trap. Regardless of what series or type of steam trap you are looking at, steam traps work on differential pressure. Without differential pressure, steam traps will not drain condensate. The trap you're looking at today is operating with 22 psi steam on our header. We're operating at around 17 to 18 psi at the steam trap. You can see the bucket going up and down and the steam bubbles coming through the bucket. Bucket traps work on a buoyancy principle. What we want to show you is how steam traps will not operate without differential pressure. Differential pressure is we must have higher pressure on our inlet on our equipment than we do downstream. I'm going to shut a valve off on the discharge side of this steam trap loop and show you how eventually that steam trap will quit operating. When the bucket is closed or in the up position, the steam trap is shut. When the bucket drops to the bottom of the trap, it opens and allows condensate to pass. It'll take a few seconds here for the pressure to equalize so that you don't have differential pressure for it to operate. You must have differential pressure in your systems for any style of bucket trap to work. That differential pressure can be affected by a lot of different things. The back pressure in your condensate return system, the piping configuration, if the discharge side of your steam traps are going vertically up 20 feet, 30 feet, that can create back pressure. So your steam traps must have enough differential to overcome any additional piping downstream and or constant back pressure in your downstream condensate return system. I'm going to open the valve back up and show you how, with differential pressure, we are now passing condensate. You can see that the condensate is passing through our sight glass. The bucket is now back in operation. It has differential pressure. We have 17 psi on the inlet, 2 psi on the outlet, and we're draining your equipment. I want to show you what happens now when you lose upstream pressure on a bucket trap and show you how no condensate will pass. Well, as your steam is shut off to your trap, the condensate inside your trap can flash off and pass live steam into your return system, which may create enough back pressure that your condensate will not drain from your equipment. When we reintroduce upstream pressure, the bucket trap will eventually fill up. The air bubbles created from the boiling water will dissipate and will eventually go back to normal operation. After all the air is out of the system, it's passed through the bucket. The trap is now working again. We're draining your equipment, passing condensate. Okay, we would like to now demonstrate a float and thermostatic type steam trap. Again, different style of steam trap, but still requires differential pressure to operate. No differential pressure, do not drain condensate from your steam lines or your steam equipment. Again, we're operating at the 22 psi, 17 pounds coming into our trap. We've got zero differential downstream. I'm going to close the downstream valve and build up back pressure to show you how this trap as well, high back pressure or equalized pressure upstream and downstream, do not pass any condensate. Okay, I have opened our downstream valve, showing that we have differential pressure again. We have 0 psi downstream, 17 psi upstream. As you can see, the condensate is now moving through our steam trap. A float and thermostatic trap is a much better trap to pass air. You'll inject air into the system. You'll see how the air will push the condensate through the steam trap. The float and thermostatic type trap has a thermostatic element in it that is very good for passing non-condensables, air, gas. The float mechanism handles the condensate. The thermostatic element will pass out the air. It gives you good protection for both. I'm going to demonstrate how a float and thermostatic trap is not affected by the upstream dumping of pressure. The flashing effect does not occur in an F&T type trap due to the thermic element in the trap passing off all the non-condensables. Stream pressure back on the trap goes back to normal operation. We at Schimberg Company would like to thank you for your attention and inviting us to help ADM create this video. We hope that it has been very instructional and will help you troubleshoot your steam and condensate issues at your different locations. If you need any further assistance, please contact us at Schimberg Company. We'd be more than willing to help you in looking at any problem areas in your steam or condensate return systems. Thank you very much.